Okay, I've tried to do this and it's not really working. This is the ink that I use, the toner. This is the vegetable oil. And this is the rare earth magnets that I bought from Home Depot. I looked online and this is a rare earth magnet. But anyway, here's my solution. And I kept trying it, and then I kept adding oil because the video said if it's not, like, you might need to add more, even though I only put 50 milliliters of the toner. So then I am trying it here, and nothing is happening. And then I poured it in this container. See, and I'm putting this under this rare earth, 2 of those, and it's not forming. So I'm not sure why it's not doing that. Maybe these are too small, but this is the only rare earth magnet that Home Depot had, and I went to Lowe's and Lowe's didn't have any. So yeah, I'm not sure why it's not working. And I'm just gonna show you how liquidy it is. It's very, ooh! Oh no. It's very liquidy. So, I'm not sure why it's not, the magnets are not showing up. Which I'm really disappointed because I really wanted to see it because it looks so cool. But yeah, I really tried my very best. And I made a huge mess, so we love that. This is my Interactive Advanced Concept Presentation 7, Magnetic Fluid. In this experiment, I tried to create a simple ferrofluid using common household items, ink toner, vegetable oil, and a rare earth magnet. A ferrofluid is a liquid that becomes strongly magnetized in the presence of a magnetic field. This fascinating substance exhibits both liquid and magnetic properties, making it a subject of interest in both scientific research and practical applications. The materials that I used were ink toner, vegetable oil, and rare earth magnets. The ink toner contains fine iron particles which are essential for creating the magnetic properties of the ferrofluid. Vegetable oil acts as the carrier fluid, suspending the iron particles and allowing them to move freely. The rare earth magnets provide the magnetic field necessary to align the iron particles and create the characteristic patterns of a ferrofluid. For the procedure, I combined 50 milliliters of ink toner with 2 tablespoons of vegetable oil in a container. This didn't initially work, so I added more vegetable oil because in the video it said you might need to add more. But the oil helps to suspend the iron particles in the toner, creating a colloidal mixture. Then I placed the rare earth magnet near the container. Then I observed how the ferrofluid, or I tried to, reacted to the magnetic field. If it had gone correctly, it would have formed spikes and patterns along the magnetic field lines. So let's talk about the composition and properties of ink toner. It includes particles. Ink toner contains fine iron particles, magnetite and Fe3O4 or similar ferromagnetic materials. These small particles are small enough to form a stable suspension in the carrier fluid. Magnetite is a mixed iron oxide with both Fe2+ and Fe3+ ions, providing strong magnetic properties. The formula can be represented as such, and the presence of both oxidation states allows for complex magnetic interactions. The toner often contains surfactants to prevent agglomeration. Surfactants stabilize the colloidal particles by creating a repulsive barrier that counteracts the attractive forces between particles. For the chemical and physical principles of the magnetic particles in ink toner, the toner contains fine iron particles that are ferromagnetic. These particles are magnetized in the presence of a magnetic field, which is why the fluid responds to the magnet. The toner often contains surfactants that help disperse the iron particles evenly in the oil, preventing them from clumping together. Vegetable oil is a non-polar solvent that effectively disperses the iron particles. Its viscosity allows the particles to remain suspended and move freely in response to the magnetic field. The oil's hydrophobic nature ensures that the iron particles are well dispersed, reducing the likelihood of sedimentation. When the magnet is brought near the ferrofluid, the iron particles align with the magnetic field lines. This alignment creates the characteristic spikes and patterns seen in ferrofluids. The shapes formed are due to the balance between the magnetic forces pulling the particles into alignment and the surface tension of the oil trying to minimize the surface area. The surfactant interaction surfactants like oleic acid may be used to coat the iron particles, providing a steric hindrance that prevents agglomeration, and that is the formula below. For our observations, I should have seen a spiked formation. The ferrofluid forms spikes along the lines of the magnetic field that are due to the attraction of iron particles towards areas of high magnetic flux density. The fluid remains liquid and flows normally when the magnetic field is removed, demonstrating the reversible nature of the ferrofluid's response to the magnetic field. Let's quickly connect what we've learned about ferrofluids to electrochemistry that we learned in Module 5. For redox reactions, the formation of magnetite involves redox reactions where iron ions in different oxidation states combine. These redox reactions are fundamental in electrochemistry, which studies the transfer of electrons during chemical reactions. An example of a redox reaction in magnetite formation is presented below. In electrochemical cells, redox reactions occur at the electrodes, with oxidation at the anode and reduction at the cathode. The behavior of iron particles in a ferrofluid can be likened to the movement of ions in an electrolyte, where external electric or magnetic fields influence their distribution and movement. The magnetic field influences the movement and alignment of iron particles in the ferrofluid, similar to how an electric field drives ion movement in an electrochemical cell. In conclusion, the creation of a ferrofluid using ink toner, vegetable oil, and a rare earth magnet demonstrates fundamental principles of magnetism and colloidal chemistry. The interaction between the magnetic particles and the applied magnetic field results in the unique behaviors and patterns characteristic of ferrofluids. This experiment not only provides a hands-on understanding of these principles, but also highlights the practical applications of ferrofluids in various fields. Thank you so much for listening.